Hello everyone. So student, in this video I am going to start from the electrophilic substitution reaction onwards, and this is almost the end of the topic, end of the chapter also. And after that, after this completion of topic, I am going to discuss some of the exercise question with the complete the reaction and then IUPAC naming and conversion type. Okay. So electrophilic substitution reaction. Student, in haloalkanes, haloarenes, I already told you that the last section of that haloarenes is that is electrophilic substitution reaction. The same kind of reaction is occurred in the case of aromatic ether. The same phenomenon. Here also the groups are attached to the ortho and para position with respect to the alkoxy group, right? Because the alkoxy group is ortho para directing and activates the aromatic ring towards electrophilic substitution or electrophilic substitution in the same way as in phenol. So in phenol we just completing only two electrophilic substitution. One is the nitration and other is the bromination. Now here the first reaction is of halogenation, and especially in this halogenation it is the reaction of bromination, because bromine is going to attach, right? Bromine is going to attach to its ortho and para position, and during bromination the reagent is bromine in the presence of ethanoic acid, right? And you can see this statement also. Halogenation: phenyl alkyl ethers undergoes usual halogenation in the benzene ring. Example is anisole undergoes bromination with bromine in ethanoic acid even in the absence of iron 3 bromide as a catalyst. It is due to the activation of benzene ring by the methoxy group. Para isomer is obtained in 90%. So student, I already told you that during this electrophilic substitution type reaction always there are two products. One is minor and other is major, and major is always the para product. So here the difference is only in the previous chapter the reaction of chlorobenzene is given with all this respect: halogenation, nitration, sulfonation and Friedel-Crafts reaction, and there in terms of halogenation chlorination is given. Here in halogenation bromination is there. So this is also one of the important part that during this bromination Br2 is used with respect to ethanoic acid, right? And at the same place ortho para position the bromine is going to attach. Now the next reaction is Friedel-Crafts reaction. So here also in Friedel-Crafts reaction, that is the addition of or attachment of alkyl group as well as the addition of acetyl group to its ortho and para position using the same condition, that is anhydrous aluminum chloride as a catalyst. Okay, the same reagent here we are using here also, that is CS3Cl for alkylation and CS3COCl for acylation, and at its ortho and para position in the case of alkylation methyl group is attached, and in the case of acylation COCH3 group is attached. So in previous topic also student, I already told you that you can attach the condensed form also. Otherwise if you want to expand this formula then also it is possible. Okay, so I hope the point is clear to all of you. Now the next is the nitration reaction. Once again, during the nitration the reagents are same: H2SO4, concentrate sulfuric acid and nitric acid, both the same reagent are used. Student, throughout the organic chapter during the nitration this concentrated H2SO4 and HNO3 is used, right? Either it is haloarenes or it is aromatic ether, right, or it is phenol. So generally we are using this one as a reagent. Yes, and the same ortho and para position the group is going to form, or the nitro group is going to attach. Okay, so I hope the point is clear to all of you, and this is the end of the particular topic, right? This is the last topic of this chapter, and after this topic I am going to start with some of the question, right? So here the question is related to the IUPAC naming. So student, here on the screen with name and the structures everything is given. So like 2-methyl butane 2-ol, 1-phenyl propane 2-ol. So whenever you are going to draw the structure by using the name, then always give preference to word root first. Whatever the word root is there, you just write the same number of carbon as a word root, and then you follow the numbering from any side. That is up to you. So like if here it is but is the word root, so first you connect 4 carbon and then see the attachment. At its second position methyl, okay, now 2-methyl, and at second position OL, that means OH is there, so you can put this one also, right? If you want to write these positions from right side, then also it is correct. So very simple, I already told you haloalkanes salvagins chapter also during the nomenclature. These positions are actually for any long chain. We have 2 sides to count the carbon, any 2 sides, right? Whatever the chain you are going to decide as the parent chain or the longest chain, so in that particular chain you can count from any side, and it provides 2 sides for counting, right? So whenever there is a name and we are going to draw the structure, then we have choice. We can start from any side, we can assign the number from any side. So I hope the point is clear. Similarly, now 1-phenyl propane 2-ol. A student, always keep one thing in your mind, that whenever the functional group is present, then that carbon chain is considered as the main chain. Either it contains minimum lowest carbon or the largest carbon. This is not the condition, right? The group in which functional group is present, that group is only considered as main parent carbon chain. So here if you want to see that, here in the name propane 2-ol is there, right? But 1-phenyl group is also there, in that 6 carbon is there, but that particular group is used as a branch, but 3 carbon is used as a main carbon chain. The reason is this alcoholic group is present to the second position of the chain, second position, okay? So here 1-phenyl propane 2-ol, so that propane 2-ol, now you can count from any side. At its first position you attach phenyl, and second position OH. Now third question, 3,5 dimethyl hexane 1,3,5 triol. So first again the word root is hex, first you connect 6 carbon. At its first 3 and 5, 1/3 and 5 OH is there, and 3 and 5 methyl group is there. So in this way you can assign the position of the group. First you write draw the structure of the parent chain, and then you can attach, okay? Similarly, like 1-ethoxypropane, 1-ethoxypropane, fifth one. So longest part is the propane, to its first position ethoxy, okay? But due to mistake in this structure, methoxy is given, and in the name ethoxy is there, so you just make it C2H5, right? Either you change in the structure or you change in the name, right? So in the name it is 1-methoxy, or in structure you write C2H5. So it is up to you. This is the correction in this particular solve naming. Then in sixth one, 2-ethoxy 3-methyl pentane. So student, I already told you that whenever any group, any prefixes are attached to first position, then position is not required. Otherwise, if except that first position, if anywhere the groups are present, then we have to keep their positions. So here 2-ethoxy 3-methyl pentane. So one is the ethoxy group, other is the methyl group, which are present to the pentane. So first we draw pentane, 5 carbon chain. Then at its second position we are going to attach ethoxy, that means OC2H5, and its third position methyl, okay? So don't think that always the ethers are seems to be like ROR dash, straight chain is always visible. No, it's not like that. It depends, because I already told you that ethers are always used as a prefixes, is never going to be suffix, okay? Then you can see 813 cyclohexyl 3-cyclohexyl pentane 3-ol. So now OL is at the fifth carbon, that is on pent. So first you write or draw the structure of 5 long carbon chain, straight chain, pentane. Now at its third position cyclohexyl is there, as well as at its third position OH is there, right? So this is the structure of that particular compound, right? So in this way you can complete all this structure. It is for your practice part. Okay, so I hope this structure and this naming is clear to all of you. So after this structure, I want to discuss some complete the reaction part. Write the structure of the major organic product in each of the following reaction. Student, we already completed 2 organic chapters in our video classes. So I want to discuss some of the exercise question, because in organic the questions are not based on a single chapter, single topic. That's why I wait for this second chapter completion, and now I discuss the questions from haloalkyl salivarians. So student, if you see the first reaction, just focus on the topic. It is, one is the chloride part and that is the iodide part, and acetone, dry acetone part. So if you remember, this is the formation of alkyl iodide, this is French-Castrian reaction. So what is the product? The change is only you just exchange their halogens and we get our final product. You can see it is already solved question, but yes, this is the way actually how the reactions are going to ask in the form of question. So this is one of the form for completion of reaction, right? And we are using this concept. Now for the second question, if you see, it is a tertiary alkyl halide with KOH ethanol, right? If you remember that when alkyl halide is treated with alcoholic KOH, ethanol is alcohol, and heat, then elimination reaction takes place. So it gives 2-methyl propene. Now third one, it is treated with NaOH and water. So once again I told you that if only aqueous KOH or NaOH given, so instead of aqueous water is given already, so it gives alcohol. At the same place of halogen, the alcoholic group or the OH group is going to attach. So you can see here, like 2-bromobutane is simply changed to butane 2-ol. So you can use this concept as a conversion part. Now next, alkyl halide, that is ethyl bromide with KCN and aqueous ethanol. So student, in this case the cyanide group is directly attached to the position of halogen. Now means bromine is going to remove and CN is going to attach, right? So this bromoethane is going to change in the form of propane nitrile. You can see here propane nitrile, and byproduct is KBr. Okay, similarly if you see the fifth question, see student, it is C6H5ONA plus C2H5Cl. This reaction or this question is given in haloalkane salivarians chapter, exercise question, but actually this is Williamson synthesis. The reaction is of Williamson synthesis, right? Here sodium phenoxide is treated with alkyl halide and the ether is going to form and NaCl as a byproduct. So the main product is C6H5O C2H5 plus NaCl. So you can see on the screen. Then sixth, here alcohol is treated with SOCl2. So if you remember our first process of preparation of alkyl halide from alcohols, right? Then we are using the concept that last reaction with SOCl2, right? And it gives, instead of OH you just attach Cl and the byproduct are HCl and SO2. So we are getting from this propanol to we are getting chloropropane plus SO2 plus HCl. So you can see here on this screen, propane 1-ol is going to change in the 1-chloropropane. So here we can say student vice versa type reaction. Suppose propane 1-ol to 1-chloropropane. So you are using this one. Now 1-chloropropane to propane 1-ol is there. Then how can we convert this one? So it's a very simple concept. You just add aqueous KOH or NaOH. It gives propane 1-ol from 1-chloropropane. Okay student. So I hope the point is clear to you. Then the reaction of this alkene with HBr. one in the presence of peroxide, another in the absence of peroxide. So let us see this example. So when HBr with peroxide is given, this is called anti-Marconic addition, right? So in that situation, the halogen is attached to that carbon between where the double bonds are present in between. So Br is going to attach either any one of the carbon where the double bond is situated, right? So here the double bond is in between two carbon, right? So but the condition is where the Br is going to attach. So when peroxide is given, it is going to attach to that carbon where more hydrogen is there, and if only HBr is given, peroxide is not mentioned, then it is going to attach to the carbon where less hydrogen is there, right? The position is same. The halogens are going to attach to that doubly bonded carbon, in one case where the less hydrogen, in another case where the more hydrogen, right? But the position is fixed, the carbon which involved in the double bond, right? So when we are using the more hydrogen carbon, when there is peroxide, and when there is no peroxide, we just simply attach the carbon where the less hydrogen is present. So I hope the point is clear to you. Okay, students. So these are some example. You can copy this particular conversion for your practice, right? So this is the last video before vacation also. I hope everyone got the message from our school that there is a vacation of 2 weeks, right? So after the opening of school, right, I am going to start another chapter from the first part of chemistry. Okay, and here some of the examples based on conversion, right? Solve all the assignment which is given by me, right? This is for your practice, right? And the discussion is only regarding for that part. Here you can see how we are using the different concept, right? In organic chapter, generally the topics are not based on a single particular topic, right? Always they are based on each other, on vice versa, we can say, right? It's not like that if you are going to solve the questions from haloalkanes and haloarenes, so the reactants are always haloalkanes, haloarenes, and products are always going to be haloalkanes and haloarenes. It's going to be changed, right? If you see this like benzyl chloride to benzyl alcohol, so here it is start from chloride ends to alcohol, and we are using the same concept of aqueous, KOH or NOH, and instead of halogen, that OH is going to attach. Now if you see propene to propane 2-ol, right, each and every steps is given. No need to write all this 4 structure and all. You just simply write concentrated H2SO4 and H2O with propene, it gives propane 2-ol. If you remember, during the preparation of alcohol, the first method is given from alkene, right? And 2 examples are given, one from ethene to ethanol, either from propene to propane 2-ol, propene to propane 2-ol. So there you are using this concept, right? Now ethyl magnesium chloride to propane 1-ol. So if you remember, this ethyl magnesium chloride is the form of Grignard. Similarly, for the next question, methyl magnesium bromide is also Grignard reagent. Now from this, in these 2 questions, we are going to convert this Grignard reagent to alcohol. So in one question, the alcohol is primary, propane 1-ol, it's the primary alcohol, and in the second one, 2-methyl propane 2-ol is the tertiary alcohol. Now why this one is important? If you remember that Grignard reagent only can form all the 3 different degrees of alcohol. That's why it is very much important to know about the degrees, right? And according to that degree, we have to choose the particular reagent, right? Because Grignard reagent, the common one, it can convert to primary alcohol, secondary alcohol, and tertiary alcohol, right? That's why this concept is required. So I hope I will solve the questions. If you write all this assignment part, notes part, right, during these holidays. Okay, thank you.